Hello, differential equation students. So in this video, we will see how do we solve exact differential equations. So before I go any further, let me quickly define what does it mean to be an exact differential equation. So if you have a differential equation which is of the type mdx plus ndy, where m and x are m and n are multivariable functions. In this case, the two variable functions. And then this is called exact, provided this my, the partial derivative of m with respect to y, and the partial derivative of n with respect to x, right? If these two are equal, then we say it's an exact differential equation. So let's see how do we solve. But before we solve, let's take a look at some basic terminologies and quickly review a few things, and then we will get back to solving this differential equations. Let me quickly recollect a few things in here. Suppose if you have a function f of x comma y, suppose you have a function f of x comma y, which is, let's take a look at the very simple one. X squared plus y cubed, right? Then you all know that the partial derivative of f, with respect to x, we denote it this way. And by the way, the way that we find the derivative is we treat the y as if we fix the y. The y is stationary and x is the variable, x is the moving. So we are going to fix the y. So therefore, we're going to treat the y as if it's a constant, right? And then we're going to find the derivative with x being the variable. So the idea here is, again, finding the rate of change of this function with respect to finding the rate of change of this function with respect to only one variable, right? So if I do that, what do I get as we get simply 2x, because the derivative of y, and that's a y, right? I'm going to treat it as a constant, so the derivative is going to be 0. For the same function, ladies and gentlemen, if I ask you what is the partial derivative of f with respect to y, again, I'm going to treat the x as if it's a constant. I'm going to only do the derivative with respect to y. When I do that, I'm going to have a 0 plus 3y squared. I'm sure you have done many of these problems before, so that's how we would find the partial derivative, right? Let me bring this function here. Suppose if you have another function, just in case, now let's take a look at another function. Suppose if you have another function, just say f of x comma y. Just say I have another function f of x comma y, which is x squared e to the y, right? Then how do I find the partial derivative? The partial of f with respect to x is going to be, again, I'm going to treat the y as if a constant, so therefore I'm going to treat the entire e to the y as if it's a constant. So then I would have 2x e to the y. Now here we have two functions multiplied together, right? X and x squared and e to the y. Since we are treating y as if it's a constant, it's not a big deal. We can just leave it like that. But if this also involves some sort of an x, then we would have to do the product rule. So the partial of f with respect to y would be, again, we're going to treat the x as if it's a constant. So x is the function of x is being multiplied, so it's going to remain as is, and then the derivative of e to the y is e to the y. So that's how we would do the partial derivative. Now let's take a look at what does it mean to be a total derivative and see how do we solve that. So what is a total derivative? Suppose if you have a function t of if you have a function, let's just say x comma, just times, I'm just going to give a very simple one, xy, right? I have a function, I'll just say my function is, let's call this as f of x comma y is xy. I want to find the total derivative. So one of the way we denote them as df, right? Which is also known as, if you want to rewrite it as a dxy. Remember here, I'm not saying not dxy, it's the df of xy, which is same as saying, d of x times y, right? Again, if you recollect, I'm not saying with respect to what variable we are integrating. Here, if you see, this tells me with respect to y, this tells me with respect to x, but here I'm not saying anything, right? It's just a total variable. So now you look at the variables that we have, and then the way that we write the total derivative is generally this is the following. You would say this would be equal to the partial of f, since it's a two variable, partial of f with respect to x times dx plus the partial of f with respect to y times dy. And this is called the total derivative. So this is, so we have, if you want to write it, this is the d of f of xy, or df, whatever you want to call it. So that is what we call the total derivative, and these are very, very important. And by the way, if you take a look at this one here, what you see here, if you take a look at here, the way that you see here is you have a function multiplied with a d to dx, and you have another function multiplied with a dy, and that's the kind of thing that we have. We have df partial of f with respect to x, and multiplied with the dx, multiplied with the dx, and here's a partial of f with respect to y multiplied with the dy, right? You see that. And this is called the total derivative. Let me give you another example so you can kind of follow easily. Suppose if I have another function. Oh, by the way, I did not do this example yet. So if the function is, x comma y, right, then what would be the total derivative, right? If the function is x, y, what would be the total derivative? Let's take a look. So then here this would be d of so here d of xy, right, would be the partial of f, which is this one with respect to x, which we just very similar to what we did earlier, and that is going to be simply y multiplied by dx plus the partial of this with respect to x, so with respect to y, which would be simply x. So we are going to have then x times dy, right? So that is how we find the total derivative. Let's do another example, and then we'll see how things will go. Let's try to find the total derivative of the following function. Let's take a look at a very simple. Let's not get into too crazy. Let's just say x times y squared minus 1, right? How do you find the total derivative? Again, the idea is this simple, as we said earlier. We're going to find the partial of this with respect to x, right? And then we multiply by dx. So let me write down the formula here. So if I write down the formula, the partial of that function with respect to x times dx, the partial of that function with respect to y times dy. Now, if I apply this, so what I'm going to have is the following. I would have partial of this with respect to x would be simply y squared minus 1 times dx, and the partial of this with respect to y would be x times, x is multiplied, so it's going to be minus this as 2y and dy, right? And this is called the total derivative, right? This is called the total derivative, and this is very, very useful for us, what we are going to do. Now, let's take a look at a curve, not necessarily a function. Let's take a look at a curve, and how do we convert that curve into a differential equation? Let's take a look at a very simple curve, an equation of that form. So, for example, we all know that x squared plus y squared equals 1 is a circle, right? It's a curve, it's a circle. And I want to see what kind of differential equation, right, will this curve what kind of differential equation for this curve will be a solution? How do we figure that kind of an equation, differential equation? So one of the way that we can do is, implicit derivative. If I do the implicit derivative, I'm going to say, let's differentiate this with respect to x. Let's differentiate this with respect to x. With respect to x, then the first term, this term would be simply 2x, and the second term, this would be simply 2y times y prime by the implicit derivative, and then you're going to have equal to 0. And then if you solve this, right, if you simplify this, then you're going to have y prime plus x over y is equal to 0, or if you want to say, you can say this is y prime is equal to negative x over y, or if you want to write it, you can say, you can also say x plus y prime is equal to 0, and so on. So anyway, the point that here is the solution to this differential equation is going to be this curve right there, right? So that's how we find differential equation differential equation for which this curve will be a solution. But if we rewrite it in the total derivative sense, what this would be. So what I'm going to do now, I have this. Now I have this function x squared plus y squared equals 1 is a constant. I'm going to do the total derivative on both sides, right? I'm going to do the total derivative on both sides. If I do the total derivative on both sides, what's going to happen is that I'm going to have d of x squared plus y squared equals the derivative of 1. In this case, is 1, but it could be anything. It could be x, it could be x squared plus y, anything, right? And if I apply the total derivative on the left-hand side, ladies and gentlemen, I am going to have 2x. The derivative of this with respect to x is 2x times dx plus, again, the derivative of this with respect to y, which is 2y times dy. That's my left-hand side. And the right-hand side, the derivative of 1 is a constant, so it's going to be 0. So now, what we have here is we have a differential equation. We have a differential equation in here, right, for which this is a solution. For which this is a solution. And there are some, and this is very, very important for what we are going to do with respect to the differential equation. So now what we are going to do, we are going to do the reverse process. When solving a differential equation, we are going to do the reverse process. So what is that reverse process? Now you're going to have a differential equation which is of this form, which is going to look like this. And then from this, how do I get there? So, we went from here to here. We went from here to here. Now we are going to see how do we go back from here to there, right? That's what solving the exact differential equation is. There is one other thing that I want to say then before I move forward. And we'll talk about the other one a little later. Now let's see. Let's go back to the definition of an exact differential equation, and then we will see how these are. So if you take a look at these equations, by the way, here this is your m, and here is your n, right? So this looks like your m, and this looks like your n. We say a differential equation, right, like this is called exact, like mdx plus ndy, right? Mdx plus ndy is exact, provided the partial of m with respect to y is equal to partial of n with respect to x. So let's verify if these differential equations are exact, and then I'll tell you why that is the case. All right. So in this one, the general form, as you see here, is m dx plus n dy, I think I made a mistake in here. This should be, I should say, equal to 0, right? That should be equal to 0, otherwise it's not an equation. So if you see here, this looks something like this. This looks something like that, right? The question is, how do we solve? That we'll worry about in a moment, but let's see if it's exact or not. I'll tell you what happens when it's an exact. So now here, I'm going to identify my m is equal to 2xy, and my n is equal to x squared minus 1. So if you remember the definition says it is exact provided that my is equal to nx, right? Provided that my is equal to nx. So here if I do the my, my is equal to 2x, and if I do the nx, which is also equals 2x, and you see that these two are exactly one and the same, and for that reason we can say this differential equation is exact, right? So we can say this DE is exact DE, right? So that's how we verify whether a differential equation is exact or not. Let's take a look at the second one. And here again, by the same token, if I write it, this is going to be m. What I have here is m and then plus n y prime. Now, so that's not really in this form, right? If you see here, that is not really in this particular form. But if you see, this looks like this. This kind of looks like this, y prime plus x over y equal to 0. So now what we can do, we should be able to rewrite it, right? Because there's what is the y prime anyway? The y prime is dy over dx, right? Because of the y prime being dy over dx, we can do using a chain rule, right? And so on. This is exactly same as, we should be able to rewrite this as x squared plus y squared dx plus x squared minus xy dy equal to 0. So basically, you're doing a chain rule in here, and which is in this form, right? Now this one is in this form, so therefore we can say our m is equal to x squared plus y squared, and n is equal to x squared minus xy. Okay, going back to here, does it satisfy my is equal to nx? Let's take a look. Let's take a look at the my. My is a partial of m with respect to y, which is going to be 2y, and nx is equal to 2x minus y, and you see that these two are not equal. So therefore, this is not an exact DE. This is not an exact differential equation. So we have looked at a case when one of them is exact. We looked at another case where one of them is not exact. Let's see how do we solve this one in the next video.